Everyone, welcome to the second unit we're covering in remote learning. I guess the third, if we count electrostatics, even though that was a continuation of what we were doing in the school year. We're now going into magnets. It's going to be a pretty short unit, probably about 3 or 4 lessons. Going to drop 2 of them this week, 1 of them next week, with a couple of assignments that'll be on Google Classroom. So magnets are really cool, really fascinating, kind of like, we've all played with magnets before. There's something really magical about them, and we're going to learn a little bit more about how they actually work. Now, I just want to warn you, we're going to not go into as much depth as some of you may want. So what I'll do is post some resources on Google Classroom that you can follow if you want to find a little bit more information about magnets. You can always also reach out to me to ask any questions. All right, so here comes the first video on magnets, magnetic properties. Enjoy.
Okay, everyone. So welcome. Here I have what's called a disk magnet. It's called a neodymium magnet. It's a rare earth magnet. It's very strong. And I have the 2 sides labeled. Here I have the south side of the magnet. We should all know that magnets are a north side and a south side. And here I have the north side of the magnet. Okay, so right now this thing has an impact on certain types of materials around it. Certain types of materials like other magnets. So here I have an identical neodymium magnet. However, with this magnet, I do not know which side is north and which side is south. But we've all played with magnets before. I'm sure you're familiar with how we can determine it. Well, as I hope you remember from the past, when it comes to magnets, we know that likes repel and opposites attract. So let me go ahead and take this north side, and I'm going to push it towards the south side. So now here, what I'm noticing, and you can probably see, they're not really going together. They don't really want to too well. But if I just take this one, the unmarked one, and I flip it around like that, boom, snaps together, right? You can see how strong those neodymiums are, right? They snap together. So what that tells me is that this side is attracted to this side, which means that if this was north, this one right here must be south, right? That north is being attracted to that south. Let's see it again. Ready? Watch. And there it goes, right? North and south, prime apart, being attracted to one another. Cool. So now there's really no surprise that 2 magnets would be attracted to each other. But what I want to look at now is a paperclip. In fact, I have 2 paperclips here. And if I take these 2 paperclips and stick them together, it comes as no surprise that when I drop one, right, I'm going to hold them together, it falls down, right? Nothing surprising there. But if I take my magnet that I had before and I attach the paperclip to it, there we see it sticks, right? The paperclip has stuck to the magnet even though it doesn't stick to the other non-magnet, the other paperclip. If I flip this over, instead of attaching it to south, I attach it to north, right? It sticks, or attach it to south, still sticks, right? So the paperclip doesn't really seem to discriminate against the different sides of the magnet, unlike the other magnet. What I find even more interesting, though, is we can all agree that this paperclip that I have attached to the magnet right now is not a magnet. This thing is not a magnet at all, and there's your proof, right? It's not picking up the other paperclip. But once I take it and I attach it to the neodymium magnet, you watch this. I'm going to go up to this paperclip, touch it, and lift it up. Right? Now, went to the magnet. Now, it's pretty clear that the paperclip that's now on the magnet, right, that first paperclip, is in fact a magnet itself. It's able to hold on to the second paperclip, even though, as we saw, it itself was not a magnet. Ready? Watch. I'm just going to take it off to prove this. Ready? Watch. Oh, it's still a magnet. Look at that. It's still holding on to it. Just give it a moment here. Holding on for a while. Spin it. Yeah, see, it's still, oh, there it goes flying off. But now, watch, I'm going to try picking it up. It doesn't work anymore. Suddenly, this paperclip is no longer a magnet. So, a couple different things here. A magnet that stays a magnet and repels other magnet. Here, a paperclip, which is not a magnet until it's on a magnet, and then suddenly it acts like a magnet, and an object that doesn't seem to be a magnet. But I can flip these paper clips and do the same demonstration with either one, and they should stick. Oh, that's fine. Okay. Right. Still works. So with that, let's get into what is our aim. Why does the paper clip that is not a magnet attract the other paper clip, which is also not a magnet? And to start that discussion, I just want to go back to this. Obviously, we're talking about magnets, right? North and north will repel each other. South and south will repel each other. This magnet that I drew is called a bar magnet. It's different than a disk magnet, but it's still, we can say, polarized, right? It has two separate poles, a north pole and a south pole. Likes repel. Here, north, same magnet. This one I flip upside down, so south is on the top and north is on the bottom. Here we have opposites attracting. All stuff I'm sure we know from the past. Now let's start to explore some stuff that's a little bit new, or potentially new to us. I don't want to lose that. Put it right up there. The first thing I want to talk about before we directly address the aim, in the path to addressing the aim, is a question of, what if I break a magnet? What will happen? So suppose we have another bar magnet. Okay, and this bar magnet has a north up here and a south over here. And I take it and I snap it in half, all right? So there's a nice cut down the middle there. And then I separate these two things. So I have a north here with my little cut there, and then a south over here with that cut right here. So north was here, south was here. Snap in half, two halves. Well, when I do that, what I'm gonna find is that I have a south here and a north here. So from one magnet, I've gotten two magnets. Both are polar, meaning there's a north and a south pole. Then I can do this again, snap it again, right? Crack it right down the middle there. So I have a north here, and here I have my south side, right? North, south. Well, what I find now is that there's a south here and there's a north here. So I've broken this thing again, and I've ended up with two new magnets, from 1 to 2, and now from 1 to 2 more. And if I did this, I think you can see that it would be the same result. I would just keep having smaller and smaller and smaller magnets. Now, each of these magnets that are broken will be weaker than the magnet that came before it, but they will still be magnets that have two poles, a north and a south. Now, this is really important. The word for this magnet that has two poles is a dipole. We should be familiar with that word from when we did electrostatics, and what it really simply means is it's a pair of poles. And we're talking about opposite poles here, right? A north and a south. If I keep on breaking this thing down, I'm going to be able to actually break it down further and further and further until I reach something called a domain, which is a collection of electrons. And then I can break that domain down into an electron until I reach that electron. And even that electron we will find has a north and a south pole. It has a magnetic property. Well, that means that a magnet can only be a dipole. I can't have a monopole. I can't break that electron into two things. It's not possible. Okay, but monopoles are still important. Not for magnets as much, but for charges. We've seen systems, monopole systems before, with something like a single electron, right? That single electron, if we're not talking about the magnetic portion of the electron, but just the charge, or a single positive or a single negative charge, is a monopole. So this is going to be a single pole. And we'll put charges can be monopoles. And then just to make it really clear, magnets can't. Magnets cannot be monopoles. So I just keep breaking this thing up until I get to that electron, and I still find that I have a magnet that is a dipole, even though it is a monopole with respect to the charge itself. Now, magnets are often, the strongest magnets that we deal with are made of something called a ferromagnetic material. Okay, they're made with this thing called a ferromagnetic material, and these are substances that are strongly influenced by an external magnetic, I'm going to throw a word at you here, field. We don't know about magnetic fields yet, but you know about electric fields, so I hope it's not too much of a stretch to just mention them. The next lesson will be about these magnetic fields. Now, what makes something a ferromagnetic material? What makes it like worthy of this title? A lot of it's going to come down to this idea of those electron spins that I was talking about, and then those domains of electrons. The domain is like a clump of electrons within the material itself. So sets of electrons, big groups of them will form so that they all have the magnetic quantum property, which is called spin. You should be familiar with it. Spin is what's responsible for the magnetism of the electron. All of those electrons in a domain will have a spin oriented in the same direction, and so then that domain will be a magnet itself. And then when you combine all those domains together, if those domains spin in the same direction on average, you end up having a magnetic material. Now, a ferromagnetic material has those domains, and the spin of the domains and the electrons are easily influenced by an external field, which means that the macroscopic material is easily influenced by an external magnetic field. Now, I'm going into a lot more detail about those domains and electrons than you need to know. I will post some links that will give you that bit more information if you're really interested, or I'd be happy to answer questions during the lesson recap. Now, there are two types of magnets that we're going to discuss. So there are two types of magnets that we're going to discuss. The first one is like the neodymium that we looked like. This neodymium magnet is what we call a permanent magnet. Okay, and a permanent magnet is a material like this one here. This is a ferromagnetic material. I should add that ferromagnetic material, the common examples are iron, which you probably get from this right here, Fe, right? That's iron on the periodic table. We have cobalt, and we have nickel. Okay, common ferromagnetic materials. Those are the big three. So permanent magnets are materials that act as magnets even in the absence of an external magnetic field. Wording that a little bit differently, since we haven't talked about those magnetic fields yet, what I'm saying is that this neodymium, which has a magnetic field of its own, it has a magnetic influence around it, just like a charge has an electrical influence around it. This thing doesn't require there to be another object. So this neodymium is still a magnet even when this one is absent. It's always going to act as a magnet unless I change its properties. Then there's something called a temporary magnet. And this is a material that acts as a magnet when in an external magnetic field. And what's a good example of this? A paperclip. Right? My paperclip, when it's attached to this permanent magnet, my neodymium permanent magnet, this thing has a magnetic field around it. When this paperclip is not around that magnetic field, it experiences, it demonstrates no magnetic properties really on the macroscopic scale. When I put my permanent neodymium on it, suddenly this thing is becoming a magnet. It's a temporary magnet, and therefore it can attach that paperclip to it. Okay? So there's the answer to the aim. Again, to talk about the real details of why this is happening, to really, really address this question, we'd have to talk about the electron spin, that quantum property of the electron, and the domains of the electrons within the material. But it's a bit more advanced than we have to get into, so I'm not gonna go into the details too much. All right, so I hope you found this to be helpful, and keep an eye out for the next video.